So, um, I'm using MS Paint because why not? And in this lesson, we're going to be talking about continuity. So, 1.8 continuity. So, the idea here is we want to talk about when a function is continuous. And this is an idea that actually comes up in high school level math, right? You're used to looking at a graph and saying whether or not that graph is continuous. Well, a what we learn in school is that something like this is continuous, so a nice parabola, right? That's continuous. But something isn't continuous when it has a break in it. So, if I remember correctly, high school says that a function is continuous if you can draw it without lifting your pencil. And so that's kind of the issue that we have in front of us right now. The one on the left is continuous because I could draw it without lifting my pencil. However, the one on the right is not continuous because in order to draw at the x value 0, I split up where I was going, right? Um, so this is the older idea of what continuity is, in the sense that we've, dealt with that theoretically already. Well, this is a perfectly valid way of thinking about continuity in the sense that it should directly inform your intuition about what's happening here and what to do, right? So if you draw this function, or if you think of the function x squared plus 2x minus 1, something, I just picked the numbers up at random, but you think of that function and you draw it and you're like, oh, well, that's just some parabola, and I can draw that without lifting my pencil. So yeah, that function must be continuous. And that is true, right? So your intuition is going to serve you very well. That idea of drawing it without lifting your pencil is how you should be thinking about continuity. However, in well, once we hit calculus and for all of math past this, we have a new idea for continuity, the actual genuine definition of what it means for a function to be continuous. Well, let's talk about our conversation with limits from before. So, as we've been doing, so let's consider, right, limit as x goes to 1, let's say. Now because I didn't write plus or minus either one of them, if I just write limit as x goes to 1, then that means this is the two-sided limit, right, of, if we say our function f of x, where this one is f, and let's actually go ahead and name this one g. Well, our conversation about limits says, okay, well, if this is the x value 1, that mark right there, then what we should be doing is looking on the left and on the right, where we come from as we get close to that value, right? So from the left of 1, we're heading towards this value. And from the right of 1, we're actually heading towards that same value, right? Either way that we're heading to the same point. So this two-sided limit agrees and is equal to that value that they're both heading towards. Now, oh, undo, sorry. I guess there's a reason MS Paint isn't common for this kind of thing, huh? Well, so as we head towards the x value of 1, the function is heading towards the same value from the left and the right. So this limit does exist, and in fact, if this is, a nice enough parabola, maybe this is 2, at that y value. So let's say this limit is 2. Great. Well, our new idea of continuity is actually going to be trying to say something about the limit at a value and what the function actually evaluates to at that number, right? Because for any nice function, or not any nice function, but for most of the functions that we look at, taking the limit is actually going to be doing the same thing as just plugging the number in, right? Anywhere along this parabola, it doesn't matter where exactly I'm looking, but from the left and the right, these limits agree. Anywhere on this parabola, my limit looks exactly like just looking at the function at that value. Well, that is because the parabola is the calculus definition of continuous. And that idea, if I can erase this, we consider to be continuous at particular values. And I wish the eraser was bigger. I don't remember how to change that. And we say a function named f of x is continuous at x equals a, an x value of a, if the limit as x goes to a of f of x, so the two-sided limit that we take normally, right? If that that limit is equal to f of a. So a function is continuous at an x value of a if the limit as x goes to a of f of x is equal to just plugging that number in for the function, right? So as we saw before, like with any parabola, the whole point that I was making is that any limit on this graph is going to look the same as just plugging in the number that we head towards, right? So yeah, it turns out at every x value, this parabola is continuous. And before I draw the next graph, we'll also give one more definition. Uh, we say a function is discontinuous at a if it is not continuous at a, right? Um, it's just kind of the moment where, yeah, sure, it really isn't a new definition as much as it is just saying, well, if it's not continuous, we call that discontinuous as well. Um, so, yeah, that's not too much of a horrible new term to learn. Now, the next piece, using these definitions, let's actually, oh my goodness. So, using these definitions, let's look at this graph of a piecewise function. So let's say f of x is equal to x squared plus 1 as long as x is less than or equal to 0, and then it's equal to minus x everywhere past 0. So if we were to graph that, of course, at 0 is kind of this focal point, and x squared plus 1 is a nice parabola that starts here at 1 and then is going to look like that. And then to the right of 0, we look like the line negative x. So if I plug in 0 to that, I'm 0. And then I just go down like this, right? Okay. So am I continuous? So is f continuous? And it's often you see it abbreviated CONT. Is f continuous at negative 1? So this is just asking, is the limit as x goes to negative 1 of f of x equal to f of negative 1? Well, that value negative 1, if it's here, we see it's right here, right? So I know that this limit, we can see this graphically, limit as of, the limit as x goes to negative 1 of f of x is going to happen to be, uh, well, we can see it graphically, so bear with me. If I know it's going to evaluate exactly at that value. So I'm kind of already pretending it is continuous to make this claim, but we can see graphically that it is. So the limit as x goes to negative 1 of f of x is going to be 2, the same value as plugging in negative 1 into that function, right? Negative 1 squared plus 1. So 1 plus 1, 2. Great. Is my function continuous? Instead, let's ask the same thing for positive 1. Well, that is just asking almost the same question. Now, is the limit as x goes to positive 1 of f of x equal to f of 1? Well, also, if we look on our graph over here, if this is our x value 1, then, well, yeah, the limit as our function goes to that dot is going to be exactly that dot. So the answer here is yes. However, is f of x continuous? I just should abbreviate. I don't know why I have so much trouble spelling continuous. Is f of x continuous at 0? Well, that's saying is the limit as x goes to 0 of f of x equal to f of 0? Well, f of 0, right, because that relates to this portion of the function, I need to look at x squared plus 1. So f of 0 is actually going to be 1, right? I plug in 0, 0 squared is 0, so just plus 1. However, the limit as x goes to 0 from the left of f of x, right? If x is less than 0, then we look like this part. So that is going to look like 1. However, the limit as x goes to 0 from the right of f of x, we need to be looking at this part of the function, right? We need to be looking at here for the right-hand limit. Well, this is going to just be 0. So, remember, if we're talking about the right-hand limit, limit as x goes to 0 from both sides of our function, it exists if and only if the right and left limits agree and exist on their own. Well, do they exist? Yeah. Do they agree? No. The right-hand limit is 0, the left-hand limit is 1. So the two-sided limit we have to say does not exist. So is this equal to 1? No, it is not. So this is an instance where can you say that this function is continuous at every value in its domain? No. We can plug in 0. F of 0 makes sense. That is okay to do. But it doesn't agree with the limit at that value. How could I change this to make my function continuous is a totally different question, but I need this left part here, where my function is to the left of 0, to match where I am to the right of 0. So I have two options. Maybe I say, okay, well, let's bring this line up, or I bring the parabola down instead. Either one of those changes could make the function continuous, but they would need to match. So let me redraw a totally new graph that is a piecewise function, but also happens to be continuous, and almost the same thing, but is continuous, would be something like this, right? Coming from the left and the right, I'm approaching the same value, even at 0, even at that weird point where we change what function we are, but I can draw it without lifting my pencil up. And the limit agrees with just plugging the number in. So that is what it means for a function to be continuous. So now, this example actually gives us something really interesting. We have this function that on the left limit, right, I am equal to 1, and on the right hand limit, I am equal to 0. So the two-sided limit doesn't agree. However, so we can't be continuous because the limit doesn't even exist. However, this value of the function, right, does match with one of the sides of the limits. Can we put this with a side of the limit so that we're kind of continuous on that side? And the answer is yeah. From the left, I do match evaluating exactly at that value. So even though my two-sided limit, right, does not exist, so f of x is not continuous at 0, we kind of are, but only from the left side, right? This left-hand limit does match the function at that value. So it turns out that we do say if a function is continuous on the left or on the right. So a function f of x is left continuous at a if the left-hand limit, the limit as x goes to a of from the left of f of x is equal to the function at a, and then we say right continuous. A function is right continuous if the right-hand limit agrees. So which is this? Well, even though f of x is not continuous at 0, f of x is right. Sorry. Which limit agrees? The left-hand limit agrees. So our function is left continuous at 0. So being left or right continuous is a little bit of a weaker condition than being full on continuous at that value. So can we say is f of x left continuous at something like -1? Well, sure, right? More than just being left continuous, we are also right continuous, and we are also therefore just regular continuous at that value. So I can even say right and left continuous gives me just regular continuous, right? That's supposed to be an arrow. And if I already have that I'm continuous, well then it turns out I must also be left and right continuous. So I can make that arrow really go both directions. If I'm right and left continuous, well then I'm continuous. If I am continuous, well then I must be left and right continuous. So that's useful. And that's where these piecewise functions really come into play. Okay, very good. So another idea that this piecewise function actually gives us a really good picture of is types of discontinuity, right? Because compare this piecewise function to something like uh, 1 over x. So when I graph 1 over x on the left side, I look like that, and on the right side, I look like this, right? So neither function is actually going to be continuous at 0, right? If I try and do limit as x goes to 0 of my function 1 over x, right? Then, well, from the left, that's negative infinity. From the right, that's positive infinity. So these limits don't even agree. So yeah, it doesn't exist if it goes to infinity, but even more so, it doesn't even go to positive or negative infinity. That two-sided limit doesn't exist. I can't really say anything in particular about it, right? Also, 1 over 0 on its own does not exist. So even though I can't even, right, plug in either side, yeah, it's kind of true to say the limit of 1 over x doesn't exist. We write it equals doesn't exist, and plugging in 0 doesn't exist. But we don't get to say something that doesn't exist equals something that doesn't exist, right? They just don't exist. So we can't even compare those values, right? So this is not continuous at 0, right? Because it doesn't exist, neither even does the limit. Um, okay. However, the way that it is not continuous, the discontinuity at both of these are very different, right? Because this is kind of like the function just moved up a little bit, right? It would be really easy to fix that. However, this is not something that I can easily fix. This is going up and up and up and up to positive infinity forever and ever and ever. This is going down and down and down and down to negative infinity forever and ever and ever. So it is useful to differentiate between these different kinds of discontinuity. So with this function here, this is actually what we call jump discontinuity. Oh, my handwriting looks horrible and I misspelled it. Jump discontinuity, right? Because the function jumps from one value to the other. However, here with our 1 over x, we call this infinite discontinuity. Because these values are like infinitely apart, right? We're going to infinity on one side. Um, Now, this also happens anytime we have a vertical asymptote. So let's kind of compare this um, to like 1 over x squared, right? So the graph of this function is actually only ever going to be positive, and we also are discontinuous, but in kind of a different way, right? We're not heading off to two different directions, but the limit as x goes to 0 of, sorry, 1 over x squared is infinity. Now that is not a number, so it does not exist, but it is useful to say that it increases without bound. So we say it's infinity, but it still doesn't exist. And again, can I do 1 over 0 squared? No. I meant to just say no. I don't know why I wrote the T. No, we can't do that. So again, this is another function that is discontinuous in exactly the same way as the 1 over x. Though that limit at 0 looks a little bit different, and the function looks, well, I guess a lot different. This is also infinite discontinuity. And really we mean at 0, right? Okay. Well, there is, so far we've talked about jump discontinuity where the function just suddenly raises. Infinite discontinuity, which is wherever there is a vertical asymptote, right? Values are going off to infinity. But there is a third example of discontinuity, and let me come up with a function for that. That is something like x squared minus 1 over x plus 1. Oh, not what I meant to do. There we go. So this, right, looks like the function, right? I can factor x squared minus 1 into x minus 1 times x plus 1. And so if x is not equal to negative 1, right? Because otherwise the denominator would be 0, and I can't have that. Then x squared minus 1 over x plus 1. The plus 1 is going to cancel on top and bottom, and it's going to leave me with x minus 1, which really means that the graph of this function is going to be x minus 1, except I cannot plug in negative 1, right? I can't plug -1 into this function. So there's going to be a hole at -1. And then to the left, we're going to continue. So this is discontinuous, right? Because the limit as x goes to -1 of this function here is actually going to be -2, but f of -1 does not exist. So these are not equal to each other, and therefore not this function is not continuous at -1. But now this is a very different way. Our function didn't jump like we did there. We don't have a vertical asymptote like we did with dividing by 0 at those other values. Here, it's like we just have a hole in the function. And this is what we call removable and sometimes even called hole discontinuity, where oh, where the function earnestly has a hole at that value. That's the most complicated thing going on. It doesn't jump, there's no asymptote, it just can't plug in that value. Otherwise, we look nice and fine. Okay, the following classes of functions at all values in their domain. And so the first one are polynomials. Something like x to the 40th minus 20x squared plus pi x, right? Any polynomial is going to be continuous. So our limit at any value is going to just be the same as plugging that number directly in. Next, we have rational functions. Those are the ones that look like some polynomial over some other polynomial. So something like x squared minus 1 over x cubed minus 11. Well, hold on, this feels weird, right? Because if you draw this graph of a rational function, it might have holes or asymptotes in it. And oftentimes they will have asymptotes, right? Um, and this does not match this function at all, but I'm just making up some rational function. It could look like this. Right? Something like that. Well, again, we care about what values are in the domain of the function. The following classes of functions are continuous at all values in their domain. So even though we have these asymptotes where, yeah, we have to lift the pencil up, we don't have those numbers in the domain at all, right? So we don't even care that they're not continuous at that value because I can't plug that number into the function. So even though these are asymptotes, we still say they're continuous at all values in their domain. Okay, very good. Now the next class of function are roots. So something like a square root or even a cube root. Now these are very different, right? The cube root and a square root. For one, well, the domains vary greatly. The graph of a square root is going to look like this, right? But the graph of a cube root actually will include negative values. I'm really impressed with how accurate that graph is. I know that may not stand out to anyone watching this, but that is a very good graph. I'm proud of myself. Anyway, right, even though the square root can't take negative numbers, right? This doesn't even exist at negative values. The cube root does. So they're kind of different, right? Square root, cube root, fourth root, even roots, and odd roots have different domains. But any root function is going to be continuous at all values in their domain. Okay. Um, so very good. I think there's a couple more that the book lists, um, but a lot of the exercises are going to be asking you to prove that functions are continuous by looking at the limit and seeing if that is equal to the function at that particular value. Okay, so very good. I think that is enough for some part one, at least of 1.8. Okay, I don't know how to say I'm done, so I'm just gonna stop. Bye bye.